So in 10 minutes, I want to show you a long-standing open problem and some recent results which do not solve the open problem, but which are motivated by it. And all of this involves the space of immersed two spheres in R3 and the Willmore energy. So the space of immersed two spheres for this talk will be the maps from S2 into Euclidean 3 space, which are smooth immersions. So elements of this space are, for instance, the standard embedding of S2 into R3. And S2 is an orientable surface, so we can fix an orientation on S2 and indicate the orientation of the immersion by coloring the two sides of the immersion or by drawing a small oriented normal. And but other than that, we also have more complicated immersions like this immersion on the right, which can have complicated self-intersections. So if you allow me, I actually have brought a 3D print of this, so I won't miss this, but I forgot it. So this is the surface, and we'll come back to that later. And one important result about the space of immersed two spheres in R3 is that of Seidel, which says that any two immersions are regularly homotopic. So there's a regular homotopy between them, regular meaning at each time it's an immersion. So you can think of it as a path at the space of immersed two spheres. And at the time, this was surprising because it also implied that between the standard embedding of S2, and we call it a round sphere, and every reparametrization of that is also a round sphere. So because between the standard embedding and the embedded sphere of opposite orientation, there's also a regular homotopy. And the result by Seidel was purely abstract, so at the time no one knew how to construct such a regular homotopy between two spheres of opposite orientation. And we call such a regular homotopy a sphere inversion. Okay, but first let's throw the Willmore energy into the mix. So the Willmore energy, you can think of it as some kind of bending energy of the surface. And it's defined as the integral over the squared mean curvature. And some facts about the Willmore energy are that the absolute minima of the Willmore energy are the round spheres. They have 4 pi Willmore energy. And apart from those, there are no more critical points of the Willmore energy until an energy level of 16 pi. And at 16 pi, we have several critical points. And going back to the sphere inversion, there's one important result by Max and Benshoff, which basically says a sphere inversion has to get complicated at some point. And more specifically, it says that any sphere inversion contains at least one quadruple point, meaning that there is a time in the sphere inversion and a point in R3 where 4 sheets of the immersion meet. And intuitively, if an immersion self-intersects, it has to bend to come back to meet itself again. And this is formalized by the Li-Yao inequality, that you need a lot of Willmore energy to construct self-intersections. In this case, an immersion with a quadruple point has to have Willmore energy at least 16 pi. So this means any sphere inversion at some point has to have Willmore energy at least 16 pi. And this led to the so-called 16 pi conjecture by Rob Kazan in the 80s, which states that there is an optimal sphere inversion in the sense that there exists a sphere inversion which does not exceed this necessary level of 16 pi Willmore energy. And the idea why this should work is the following. It uses Willmore flow, which is the gradient flow associated to the Willmore energy. And it uses this surface here. This was found by Morin to construct a sphere inversion earlier. And it uses this nice symmetry it has that if you turn it by 90 degrees, you obtain the same surface, but of opposite orientation. So you just need to find one regular homotopy to a round sphere. then you turn it by 90 degrees and repeat the same regular homotopy, you obtain a round sphere of opposite orientation. You stick those two together and you have your sphere eversion. So the idea was, and then Rob Kasner found an exact parametrization of a surface which has the same type of self-intersections and the same symmetry, but is also a critical point of the Willmore energy, and has Willmore energy 16 pi. So this is what we're looking at. This is a critical point of the Willmore energy at 16 pi. So the idea is to start here, perturb it slightly to get below 16 pi Willmore energy, and then we are not a critical point anymore. We can start the Willmore flow, and hopefully we arrive at the round sphere. And then we do the same thing in the other direction to arrive at the sphere of opposite orientation. And the first step, the perturbation, this is fine, this works. It was recently shown by Jonas Hirsch and Elena Beda-Baumdicker. They computed the index of this critical point to be 1, so we can perturb it. But you already see the big question mark is behind the convergence of the Willmore flow. We do not know that the Willmore flow does converge to a round sphere. And in the 90s, there was numeric simulations which suggest that this should work. So on YouTube, you can watch a video of exactly a sphere version constructed by Willmore flow with a discretized version of Willmore flow. But since then, there's no analytic proof that the Willmore flow actually behaves nicely and converges to a round sphere in this case. So the problem is the convergence of the Willmore flow. What do we know about the Willmore flow? There's one result by Kuvert and Schätzle which states if we start below a Willmore energy of 8 pi, then everything is fine and we converge to a round sphere. So that's at least some part of the way we have to go, but between 8 pi and 16 pi we still have no idea. And actually there are examples of initial surfaces arbitrarily close to 8 pi but above 8 pi whose Willmore flow does not converge to a round sphere, so whose Willmore flow does develop singularities. So we have to deal with singularities of the Willmore flow, and the question here is, can we avoid those singularities? And I want to give a partial answer to that only for the region between 8 pi and 12 pi. So what we'll see now talks about what happens to the Willmore flow below 12 pi, but above 12 pi to 16 pi we still don't know. So the results are the following. So firstly, we've seen that the result by Kuvert and Schätzle tells us that if we cut off the Willmore energy landscape at 8 pi, we have 2 valleys remaining, and in these valleys the Willmore flow behaves nicely, and in both valleys we have the round sphere of a certain orientation. But now if we cut off the Willmore energy landscape at 12 pi, the situation is more complicated, and we can actually show that we have 4 regular homotopy classes remaining, so 4 valleys remaining. So there are 2 additional valleys which do not contain round spheres. So if we start in those valleys, we are trapped and we cannot converge to a round sphere. So all of the surfaces in these valleys produce singularities with the Willmore flow. And all of the known examples, all of the previously known examples of initial surfaces whose Willmore flow does not converge to a round sphere lie in those valleys. And outside of these valleys, there still might be singularities for the Willmore flow, but what we can show is that they are not as bad. They can be avoided in a certain sense, and this is what the second theorem is about. So it says if for some initial immersed sphere with Willmore energy less than 12 pi, there is a regular homotopy to a round sphere without triple points, and then there's also a regular homotopy with Willmore energy not exceeding the initial one. So it kind of upgrades any topological description of a regular homotopy you have to a regular homotopy of low Willmore energy. And the first part of the theorem here is basically the condition that we start in the right regular homotopy class where we actually have a round sphere. And this is a nice condition in some sense because you only need a description of the self-intersections along a regular homotopy to a round sphere. And this is the situation we are in with the sphere version. And then if you start in the right regular homotopy class, we can avoid the singularities. We can flow around them in the sense that we can find a regular homotopy which keeps low Willmore energy and does not exceed the initial one. And that's all I wanted to say. So thank you for your attention.